Hi everyone, Mr. Rodriguez here with another video for you all. I hope you all are doing great, staying safe, and I hope your first week of digital learning last week went well. As digital learning requires a lot of personal responsibility, a lot of your own kind of time management, but just no personal responsibility is not the same thing as having to do it all alone. So please do feel free to reach out to all your teachers, attend Digital's live office hours, and whatnot. You do not have to do it alone. All right, so let's take a look at what we are doing today. So, our objective for today is students will be able to solve for the volume of cones and pyramids using volume formulas as well as find the area of cross sections. So you did similar sort of things already. You found the volume of some shapes in the previous lesson and also looked at cross sections. So this is kind of a continuation of that. So let's take a look at our first little problem right there. This is the volume of a right circular cone. So as you can see, this figure here kind of has a cone-like shape, almost like a birthday party hat or something. And we see it has a base that is a circle, and we see it kind of comes to a point, right? So let's take a look at how to solve for volume of this. So as always, we have a formula that we can use to solve for volume. So our formula here is going to be volume is equal to 1/3 pi r squared times h. So r again stands for the radius of the base, and height, of course, is how tall our 3D shape is. So now all we have to do is just plug in our numbers into this volume formula. First, I just want to point something out though, kind of where this volume formula comes from. So if you look at if you remember the volume for a cylinder, it was just pi r squared times h, right? And what you notice, a cone's volume is basically just a third of that. So if you kind of think about it, if you kind of look at the two different 3D shapes, you kind of notice that a cone's volume is a third of a cylinder's volume. So that's where the 1/3 comes in there. So let's take a look now. So we can rewrite the formula now with our numbers. So volume is what we're solving for, so that stays V. 1/3 is just part of the equation, right? Pi again is also just part of the equation. I'll use 3.14 for pi here, so we can replace that. So let's say 3.14. That's just an estimate of what pi is. Radius squared. So our radius here, if we look at the cone, we see the radius is right over here. Just be careful, make sure you're always using the radius. The diameter would be across the whole circular base, right? So something like that would be the diameter, and if you wanted the radius there, you would have to take half of that. But luckily here we are given the radius. So we can just simply plug that in. So we have times 3 squared. And lastly, times height. So again, we're clearly given height here. Height is 9. And all you need to do now is basically just plug these into a calculator and you'll get your answer. So let's see here. So let's say we do 1/3 You can put that in as parentheses 1 divided by 3, right? Times 3.14 times 3 squared times 9. Right? So if you put that all into your calculator, you should get about 84.78. So our answer here is, our answer here is 84.78. And that would be our volume. And to be clear, since we had inches, this would be inches cubed, or inches to the third. So that's how we do a volume of a cone. Let's take a look now at volume of a right rectangular pyramid. So this up here was a right circular cone, right? It's a cone shape, it has a circular base, and you see how those two lines form a right angle. That's why it's called that. So similar here, we have a right rectangular pyramid. So this now is more of a kind of pyramid shape rather than a kind of rounded shape. And it has a rectangular base. And again, we see how the altitude, the kind of height there, the line, right, forms a right angle with the base. So it's a right rectangular pyramid. So again, we have a formula we can use for these right rectangular pyramids. That formula will be volume equals 1/3 length times width times height. So again, let's take a little look at this formula. If you remember when you did rectangular prisms, your volume was just length times width times height. So what we notice now is that this pyramid is really just 1/3 of that, of the volume of the rectangular prism. So that's where this formula comes from. Not too mysterious. So let's see. So again, all we have to do now is just plug in our numbers. So volume is what we're looking for. 1/3 is just part of the equation. Times our length. So this now is the length of the base, right? So our length is 22. Length is the longer side, right? And then our width is 21. And again, height is just how basically tall or how high the 3D shape is. So clearly that's 35 here. And once again, all you need to do is just plug in these numbers into your formula, right? And then just put it all in your calculator. So again, 1/3 is 1 divided by 3. If you're putting it all in at once, just make sure you put that in parentheses. Times 22 is length, times 21 is width, times 35 is height. And we get, let's see, we get 5,390 as our volume. So let's say, oops, why do I keep doing that? We have volume equals 5,390. And again, this was in yards. So this would be yards cubed. So that would be a fairly big pyramid we have there. So to kind of sum up, we have, right, the volume formula for a cone up top in example 1, and we have the volume for a pyramid in example 2. Again, if you think about volume in general, all you ever do to find volume for any kind of shape is you're basically multiplying kind of like the area of the base times the height. And for cylindrical or prisms, right, sort of shapes, it's very easy. All you have to do is the area of the base times the height. With these cone or pyramid-like shapes, though, the only issue is kind of as you get higher and higher, right, you notice how it kind of shrinks, right, the amount of space. So that's where this like kind of 1/3 comes from here. That's why it's a little special here. All right, so let's look at one more example. So you'll notice here, so kind of like what we just talked about, let's just first look at this kind of figure here before I get into the problem. Do you see how the base is kind of like a large triangle, right? And then, do you see this kind of little triangle that's in the middle there? It's almost like a base that's in the middle of the pyramid here, right? That's called a cross section. So you can almost imagine if a plane kind of intersects this pyramid here, you'll end up with this kind of little shape right there, that little triangle. And basically one thing that you have to know is that this kind of triangle up here is actually similar to the base. It's just a smaller version. Same if you were to draw a triangle kind of up here, right? That would just be another kind of smaller version. And again, similar basically means that it's the same shape, just a different size. So that means the sides kind of these shapes here are proportional. So let's take a look at the actual problem now. So it says, in the following triangular pyramid, a plane passes through the pyramid so that it is parallel to the base and results in cross-section A prime, B prime, C prime. So again, it's just saying that this triangle up here is parallel to that one down here. And the altitude from V is drawn. The altitude is just how tall this pyramid here is, right? So we have V up here, right? And it says it has the intersection of the altitude with the base x, right? So we see this kind of line from here all the way to there. That's like the top to the bottom. And then the intersection of the altitude with the cross section is x prime. So we have x down here. That's, right, this point that's on the base. And then we have x prime over here, which is this point that's on this cross section, right? And then it says if the distance of x to v is 18 millimeters. So again, see how it says 18 here? It's saying that this whole distance, this whole blue line here, is 18 millimeters. And then it's telling you the distance from x prime to v. So that now is this, right? From x prime to v. And that's 12 millimeters. So, and then it tells you that the area of triangle A prime, B prime, C prime is 28 millimeters squared. So we have, right, so this area right here is 28 millimeters squared. And then it asks you, what is the area of triangle ABC? So again, basically what you have to use here is the fact that these two triangles are similar. So let's think about this a bit. So this triangle, the bottom one is similar to this one, but we kind of have to think about how do we sort of know how similar it is, or not how similar, but kind of what the exact proportion is what we're looking for. How much smaller is this triangle up here than the bottom one? And we can actually use the sort of distances, the heights that they gave us to help us here. So we noticed that the total distance, right, we said from this top, let me just delete these things here just to make it a little clearer. So we said the distance here from this top one all the way to the bottom is 18, right? And then we said the distance from this top one here, V, to this point on the cross section there is 12. So we basically noticed that this this small triangle here is basically 12/18 of the way down to the bottom. So that actually gives us our proportion. So that is going to tell us basically that, or give us a way to figure out how much smaller this triangle is than that bottom one. So if it's 12/18 of the way down to this base here, that means this triangle, or one of the sides on the triangle, I should say, like say a side here, is going to be 12/18 as large as a side kind of down there, right? One of the corresponding sides. So for instance, we have side AB, or I'm sorry, let me say that. So we have side A prime, B prime is equal to 12/18 of whatever the distance of side AB is. So, but again, that's just one side. We're not necessarily talking about the area yet. We're just talking about a side. So, another side, right? Like if we say, right, any side would be 12/18, right, as large. Another thing to point out too is that if you imagine like the heights of these triangles, like if you take this side AB kind of as the base, and if you take kind of like the height of this triangle, right, might be a little hard to see there, but if you imagine if you took the heights of both, they would also be proportional, right? The height of this top triangle up here would be 12/18 the height of the bottom triangle here. So, okay. So how does that help us find the area of this larger triangle? Well, we have to basically think about what we know about the sides being proportional. And we have to think about what the area formula kind of for a triangle is. So, let me just point out over here too. So we said if I call the height of the smaller triangle up top, let's say I called that height prime, and that's going to be equal to 12/18 of height of the bottom triangle there, right? So any kind of one side, so if we imagine like if kind of A prime, B prime is the base of this triangle up here, it's equal to 12/18 the corresponding base of the bottom triangle. And then the height right up here is 12/18 the height of the bottom one. So let's kind of think about how this will help us here. So if you remember, right, let's look at the area of the bottom triangle. That would be area equals 1/2 base times height, right? And the area of the top triangle, if we think about it, that would be kind of like, again, we could say A prime is equal to 1/2 base prime times height prime. So one thing we can kind of think about here is what's the relationship between these two triangles. So let's take a look. If we have, let's say we're going to do area of the kind of top triangle up here. So this area up here, how does it relate to the area of the bottom one? And so let's kind of say, so area of the top triangle equals to, it's going to be, again, 1/2. And then if you remember, right, we said the base, right, of the top triangle is going to be 12/18 the base of the larger triangle. And then again, the height, it's going to be the same thing. It's going to be 12/18 the height. So kind of take a second just to look at this. So we have, right, the area, this is the smaller one here, right, this is the small one over here, is going to be equal to, right, the 1/2 stays the same, but then the base of the larger triangle, right, it's going to be 12/18 the base of the larger one, and it's going to be 12/18 the height of the larger one. So let's kind of rewrite this a bit. Let's say we have, so let's just call this over here, this is, right, the area, the smaller one, this is A prime area, right, equals, again, I'm just to be clear, I'm not doing anything fancy over here, I'm just saying that, you know, this represents over here, right, the area of the smaller triangle on top, right, the area of the cross section. And we're saying that's equal to now 1/2. And then, right, 12/18 base, 12/18 height. So now I kind of just want to like rewrite this a bit. So again, we have the area of the cross section equals to, let's say we combine these 12/18 here. Let's say we multiply them together. So that would give you basically just 12/18 squared, right? And then times 1/2 base times height. Now, there's a reason I'm writing it like this. So what is 1/2 base times height? Well, this was just the, as we said up here, right? This was just the area of the larger triangle, right? The base. So really what we have is the area of the smaller one is equal to kind of this 12/18 squared times the area of the larger one. So this is kind of like, I kind of showed you a proof basically for this, this kind of formula we got here. So basically what we did was we just said the area of the smaller one is equal to 12/18 was again the ratio, right, of the heights. It was kind of 12 over, right, 18. So it's the ratio kind of the heights there, right? This triangle, we said like the side here is 12/18 as long as the side down here. So that's where that came from. And then squared, and you could kind of remember it's squared, but this is the reasoning why that I showed you up here, right? And then it's just times the area of the larger one. So let's kind of simplify this a bit more. So let's say we have area of the smaller one is equal to, let's kind of simplify this more. You could do 12 squared over 18 squared. So 12 squared, the top one would be, that would be 144 over 18 times 18, or 18 squared is 324. Times the area of the larger one. So really the smaller one is, the area is 144 out of 324, right? Times the area of the larger one. It's like 144 3/24, right? As big as the larger one. So now we're ready to just plug in our number now that we have, right? So we know up here, if you remember, the area of the smaller one is 28 equals, right, 144, 324. Hey, right? So now this is kind of just some algebra, right? We're solving for A. So first thing we could kind of do here is we can, let's see, one way we could do it is we could kind of multiply both sides by 324 first, right? So if we multiply this side by 324 and this one by 324, this cancels out there. And this side, I'm just going to rewrite it over here. So 324 times 28. We'll get 9,072. And then what we're left with over here is 144A. Now it's a bit simpler. We see we just have to divide both sides by 144. And our final answer is the area of the larger one is 63 millimeters squared. So again, to be clear here, you don't have to do all this kind of work here. This was kind of just to help you understand, right, or when you're solving another kind of problem, this was just to kind of help you understand why we end up with this kind of formula down there. But if you understand that, it's fine to just start down here. All right, so I know that was rather challenging there, but good job focusing on that. I know that was kind of a lot. So now you can kind of look down here and you'll have different kind of problems down here you can work on. This will be your classwork. Good luck, and please reach out to me, to Ms. Wesneski, Ms. Yagi, if you need any help with this lesson here.